Example problem for one of those, and we'll start by going over those. So I have a textbook. I can either pull up an example or I can just make one up. In the other class, to give you an idea of what they did today, so if you want to do something different, because I'm going to post these videos so you can watch the other class's video. The other class did an example of projectile motion. So if you want to do something with projectile motion, you want to look at that, maybe look at the video from their class tonight. I'll post both these videos today. And then in this class, we can do something different. Maybe another topic that was difficult during the year, but not the same, because it wouldn't, if I do the same thing in both classes, those videos aren't going to help each other. What do you think? What topic is something that you want to look into? Remembering that it's like 25% semester 1 and about 75% semester 2. So you still need to know semester 1 material.
So how do you think we should go about studying, like for semester 1 and 2? Like, does reading the textbook make sense, or trying to memorize the terms, especially because we don't have our tests? So
anything as far as terms and concepts, I would pull from the notes right away. Like anything that I ever ask you even on your test, every test I've ever given you, there's something about every conceptual topic in the notes somewhere. Whether I made that statement, whether it's explicitly written in the notes as for example, Bernoulli's principle is stated word for word in the notes. And notice on your last test, you had a question about that, or on the previous test you were talking about a topic in whatever it may be. But everything comes directly from your notes as far as conceptual. So that's one way to look at that. For mathematical, I would honestly review the problem set solutions. I would go to, the problem set solutions on Moodle, save all of them or something, and just sit there and go through them and recreate them. If you can't recreate it, you can't do it. So if you think that you might know something, okay, well, put it away, find the problem in the textbook, and redo the problem. And if you can redo the problem, then you check it with the answer key for the problem set, and at least you understand that topic. But if you just read through the solution sets, the solutions to the problem sets, it might not be enough. You might just be reading it and be like, oh, I get this now. But then when the actual question comes about, understanding what to do and when and how might be a little more tricky.
Do you think that we should focus more on math problems that are in the notes? Because doing every practice problem from every problems that we have.
Oh no, you couldn't.
Exactly, that's what I'm saying. So but the ones that we do in notes, they fairly similar, if anything.
If I were a student and I understood the material in circular motion really well, I might skim through my notes and that's it for circular motion. And then I would focus on other stuff. Like if I didn't know the mathematical part of forces and two-dimensional forces and did we do inclined plane? No, we didn't do inclined plane. Did we do inclined plane? I don't think I gave you a question on it though. I'm not going to give you a question on the final for that, but just a hypothetical topic, projectile motion. You need to practice math for that. Conceptual, there's a little bit to it, but it's mainly math. So for that, I would probably look at the problem sets for that. But it's topic specific. It depends on the student. So if you knew everything really well from this last test, and you think you did really well, and I'm going to give you back probably tomorrow those tests, and you might not want to study so much for that. But then study for all this stuff. It really has no one answer. But labs, problem sets, and notes. That's what I would look at. I mean, your homeworks are good to look at, but I don't correct your homeworks. You guys know that. So if your homework is wrong, you might be studying incorrect material. That's why I encourage you to look at notes and problem sets first and foremost. Then go to your labs, because your labs usually have conceptual ideas in your labs, provided they're correct. Yeah? Circular motion, want to do? Okay. What's the topic? I don't know what's in.
Optical phenomena, thin lenses, and refraction. I think we did refraction, but I don't think we did the other stuff.
We talked about optical phenomena. For example, total internal reflection is an optical phenomena. Thin lenses, we talked about diverging and converging lenses for myopia and hyperopia for farsightedness and nearsightedness. But it was more conceptual than anything else there.
Yeah, because there's equations on here.
Every equation that's on there we used. So look in your notes. Because we definitely used every single equation on there. Just take a look in your notes, you'll see where it comes from. It's probably the equation for n, I'm sure.
Yeah.
N is the index of refraction. C over V or C over V, right? V over C. C over V. Dang. I always forget which way. Steph. Harmonic motion. Okay, so circular motion and harmonic. Let's start with those two and see how far we get. Oops, that's an A. Circular motion. All right, so examples of circular motion. First, conceptually, circular motion. you have this formula, which comes from this formula. Again, if you have the acceleration, all you have to do, right, acceleration is v squared over r, multiplied by mass. Mass times acceleration is always net force. So you're given the one in blue, you need to understand to get the one in black, okay, as far as these two formulas on the board are concerned. Now, let's continue to talk about what they mean. What does v stand for? Specifically though, it is velocity, but there's something more specific. When it's in circular motion, what was the term really? Tangential velocity. Now, the reason we recall that is think back to the example from the lab where we spun an object around. When you're spinning the object around, if you let go of the object when it's on its path out here, it's going to get launched forward. And try it, remember I did a demo of this. I was holding somebody spinning it, and I would let go on the side over here, and it would shoot up. I would let go at the bottom, and it would shoot out. But it always moved tangent to the direction of the circle. So we called that tangential velocity. R stood for the radius of the circle that the object makes when it's in circular motion. What provides the centrifugal force? What provides the centrifugal force? For that example, tension. Very good. When I spin something on a rope, right, when I flip it around on a rope in circular motion, it's the tension in the rope that's keeping this in circular motion. So tension would be the force we plug in there, right, Ft. What if it was a planet around an orbiting sun? It'd be a gravitational pull. So you call this Fg instead of Fc. And you know Fg, gravitational formula for planets in motion is gm1m2 over r squared. So you could hypothetically replace this with gm1m2 over r squared. And we did that in class. That's what gave us orbital velocity when we did that. So back to the idea of circular motion though. We need to know what provides the circular motion. On a roller coaster, when you're going around a loop-the-loop, your body wants to fly off, but the normal force from the seat pushes back against you, keeps you in motion. When a race car goes around a racetrack, the force of friction keeps the tires from letting the car slide outward. So anytime something is moving in some sort of circular motion, let's say that this one is moving in a counterclockwise fashion, okay, if it's released at a given point, it will move tangent. So if it's released down here, it will move in this direction. If it is released over here, it will move in that direction. Remember what a tangent line is. A tangent line is a line that touches the circle once, only once. If I continued this blue line in the other direction, which it wouldn't make sense, but I'll do it just to see, we can see that this line continues this way, but there's only one point of tangency, and that's it right there. Okay, it's really a ray that we're looking at. These are little rays. That's a ray. That's a ray. But the word tangent line has to do with a line that touches only once. So if you want to figure out the amount of force that is exerted on a rope and see if it will snap the rope, you have to know how strong the rope can be. So let's say we have a rope that can hold up to 90 newtons of force. Okay, that's how strong the rope is. After 90 newtons, the rope's going to snap. This is very similar to what they would do when they're testing an amusement park. At what point would, the amount of force exerted on the seat by the rider and the seat and on the track be too much for the track? Probably at no point at all, but there is a yield limit. But it's some ridiculous value that it would never happen because you're using steel and metal. But if you have a rope and it's made out of like some sort of thread, right? Or maybe yarn or cotton or something that's intertwined, it's going to rip at some point. So you have some sort of maximum threshold of strength. So then you need to know some other values to see if it will or not. So maybe you're told that the mass of the object spinning in the circle is 12 kilograms. And you know that the actual radius of the circle involved in this case is 1.5 meters. So a rope that's about this long, okay, about a meter and a half. So spinning something on a very, very, very long rope that's 12 kilograms. It's going to be a lot of force here. Now, what if we're told that it takes 0.75 seconds to spin once. The time for one revolution is 0.75 seconds. How would I approach this problem? I'm not given velocity here, okay? I'm not given velocity. I'm given the time it takes, the radius of the circle, and the mass itself. I want to know what is the amount of force that's going to be felt, and if that force will exceed 90 newtons. So I need to calculate the force. I have M, I have R, I don't have V. How could I begin this problem? What could I do to find V?
Isolate V squared, so.
But remember, hold on real quick. We don't have this. This is what we're trying to figure out really. We're really trying to find FC.
I thought we have 90. Oh, that's not the same.
Well, we know that the rope can hold up to 90. We know that that's how much the rope can hold. We want to know, is the rope going to snap, is the question. The question isn't find the velocity. The question is the rope going to snap in this scenario? We have the velocity, it's just not obvious. So before we go ahead, because what Victoria was saying was, if we had 90 and we knew 90 was going here, we could solve for V and find the velocity. But I'm telling you that we have the velocity, or we have information to give us the velocity here. There's enough info. How could I find the velocity with this information alone?
Since you have the radius, can you find the actual distance and you have the time? So find the velocity and the distance that it's happening.
Yeah, so we could take the distance traveled around the circle, which is the circumference, divided by the time to give us the average speed. In this case, the speed and the velocity have the same magnitude, the same value. So you could start by doing that to make it easier. So you could say velocity, or speed in this case, we'll put an absolute value around speed to show that we're looking, or velocity to show that we're looking at speed, is really just distance over time. And this distance traveled is 2 pi r over time. Again, where does the 2 pi r come from? Circumference of a circle. The distance traveled is one circle, so that calculation can be in the numerator. The time it takes is 0.75 seconds. So we can plug those values in to give us a speed in this case, we'll say a tangential velocity, but speed works. So 2 times pi times 1.5 all over 0.75 seconds. What do we get for that? And give me nearest tenth. Nearest tenth is fine. What do you got? 12.6. All right, 12.6 meters per second. That'll be our actual average speed for this trip, which happens to be the same as the tangential velocity. So we can plug that in up here for velocity. We can go ahead and plug in the mass, is 12. We can plug in the actual radius of 1.5 to figure out what our centripetal force felt is. Mass times velocity squared over the radius. Now, do you even need to calculate this? Just look at it, please. Do you really need to calculate this? 12 times 12 alone is going to be around 144. Times another 12, we're already at like 1,000. Dividing 1,000 by 1.5 is still going to be a very large number. It will definitely exceed 90 newtons. So if this is a question where is the rope going to snap, the answer is yes right away. I mean, you can calculate the number, but it'll definitely be bigger than 90. Does that make sense what I'm saying? Okay, it'll definitely be bigger than 90. What do you get as an actual number for this?
1270.1.
Now, a follow-up question could be something like this. What would have to change? What would have to change about this problem for it to not snap the rope? And there's many answers. Give me one of those answers. What's something that could change so that the rope didn't snap? The mass. So you lower the mass. That's one way. What else? Say again? Increase the radius. Increase this radius here, which will cause the overall fraction to decrease. What else?
Lower the velocity.
Yeah, spin it slower. Take more time as a result of lowering the velocity. Okay? So that kind of approach this problem here, you can see this as like a mathematical problem with some follow-up questions or those ideas that we just talked about. How can it change? That's multiple choice. That's knowing what's directly related, what's indirectly related. Okay, tomorrow we'll start with a harmonic example, or Wednesday, we'll call it harmonic motion. On Wednesday, be prepared with questions, have topics ready, don't just sit there.